Hi class. So today we'll be looking at Unit 8, Lecture 1. So uh, we have seen a couple examples of how probability and statistics are connected. Probably the most common example we've seen is the law of large numbers. And that basically says that as you sample things with or if you look at data and the amount of data approaches a very large number, a lot of quantities begin to match the probability measures. So we saw things like the mean starts to become like the expected value, or the covariance becomes and looks like the sample covariance. Uh, Now, you may be looking at these things and think to yourself that it's not that useful because the law of large numbers only applies if n is really big and it's, not really very clear what is a big N. But we're going to look at something called the central limit theorem, which is a much more useful theorem than the law of large numbers. And the central limit theorem is like the fundamental theorem of calculus for statistics. It is the most important result in probability and statistics. And it is basically, it really allows us to use statistics in many areas in the real world because, as we've discussed, a lot of processes in nature probably don't, like, there's no reason they would follow binomial, there's no reason things would follow Poisson. But as we'll see from the central limit theorem, as you combine multiple random processes together, uh, a normal distribution arises as the number of random processes grows, regardless of how the individual random processes look. So that's why weight, which, as you can imagine, is the result of a lot of individual choices, uh, uh, the result of the genetics of people. So weight depends on what people do, what their genetics are, and yet it follows a very simple, reliable normal distribution. That deserves a wow, right? Wow. Okay, so let's see what this looks like. So, like I said, why are things often normally distributed? You look at weight, you look at, something like how much money people have in their bank account, which is actually log normal. So it's not the amount of money you have, it's the magnitude of the money you have is normally distributed. But the same idea applies. You look at height and IQ, things like that. And so here's the central limit theorem. Is when you sum multiple random variables, they become normally distributed if they have finite means and variances, and you have enough of them. This is a very low bar to pass. Most of the time when you compute means and variances, they are finite. I think in class, the only time we ever discussed something with an infinite variance was we discussed crop yields and stock market prices. Okay, so those are two counterexamples. But in general, most things have finite variance. And the other thing was is if you have enough of them. And we have this nice rule of thumb that if you have 20 to 25. Now, this is pretty wild, right? We're saying that any random numbers become normal when you sum them up as long as you have 20 to 25 of them. So let's see some of the consequences and see how this happens. So one of the most common ways we sum random variables is if we take the average of them. So the central limit theorem says that if we have random variables, like n is 20 to 25 or whatever, n can be 1. But if we take some random variables and we compute the sum, that sum of them will be normally distributed. Okay, regardless of these r's could be random variables, they could be the same random variable, we just see it multiple times. They could be different random variables. They could come from different distributions. They could be the same distribution but different parameters. There's very little required of these random variables for this property to arise. So in most statistics classes, uh, basically the professor will get up on the board and derive the central limit theorem. It's kind of a complex, I mean, it's not that complex, but it requires some tools that we haven't learned in the class, and I don't think that the derivation really drives the wonder of the central limit theorem home. So what we're going to do in our class is we're going to just see it work in practice from a couple examples. And I think it's a lot more powerful to see how this just happens. And it's one of these great things that just arises from mathematics. There's nothing about nature or our real world that makes normal distributions arise commonly. It has to do with the math, which is, kind of a thrilling result. Okay, so the name of the game here is we're going to look at a couple examples of random variables Ri, and we're going to see uh, how x changes as we change what these r's are. So our first example, we're going to sample random variables from something called the beta distribution. The beta distribution looks like this, and we don't really need to know much about the beta distribution. I'll just tell you that its sample space is between 0 and 1, okay? So notice that I didn't say anything about the sample space here. That should be pretty crazy to you, is that these Ri's, they could all be between 0 and 1. They could be between minus infinity and infinity. They could all be strictly positive. They could all be strictly negative. And yet, this x will still be normal with a sample space from minus infinity to infinity. All right, so here's an example of a beta distribution which has a sample space of 0 to 1, and it's continuous. And these alphas and betas and the z's, these are just parameters of the distribution. Actually, z is not a parameter, just as a result of what you choose for alpha and beta. Okay, so we're going to use, again, this equation. And remember, the central limit theorem just says if you sum them. So it doesn't have to have this 1 over n. It doesn't have to have an average. It doesn't need to be an average. It could be a sum. Okay, now we're going to start with just n equals 1. So in theory, the central limit theorem doesn't apply, right? I said it needs to be between 20 to 25. So we're just going to start with n equals 1, and we're going to work our way up and watch how x becomes normally distributed. So if n is 1, then basically x just equals Ri. So all we're going to look at is we're just going to look at random numbers coming from this beta distribution. Okay, and just recall, like we saw in the midterm, when I say I'm getting a random variable from the beta distribution, the actual random variable function is just the number I get out. So my random variable is the identity. Remember, random variables are analytical functions that depend on the sample space. So my sample space is the beta distribution. My random variable is just taking the output from the beta distribution, the element we got out of the beta distribution, and returning it. Okay? So Uh, I'm in Python, so I have a little bit of Python code here. So I am creating a 1000 length array. And notice that I say here, I want to talk about how x is distributed. I want to talk about x being normally distributed. To actually see that x is normally distributed, I have to look at it multiple times. Like I have to look at multiple x's, right? If I just get one number, can't tell if it's normally distributed, but if I see 1000 x's, I can make a histogram and see if that histogram looks normal, right? That's what we learned in Unit 7, is that if you have data and you want to see what it looks like, what the probability looks like, you can histogram it. And so if the histogram looks normal, then I think that the data is normal. Okay, so here we go. So I make an array to store 1000 x's. So I'm going to put all my x's into this. So I do a for loop, okay? And I basically sample something from the beta distribution. Notice I chose alpha and beta to be 0.5. We're not going to focus too much on that because the central limit theorem applies no matter what you choose for the parameters. So just those are the ones I chose. And then each time, each x, I choose it to be exactly the r. So, right, you could make each x be an average over some number of random variables, but here we only chose n equals 1, so we just basically directly take what we saw from the beta distribution, and that is our x. Then I histogram it, okay? And so here is what x looks like. Now the central limit theorem doesn't apply yet because n is 1. Remember, n has to be 20 to 25 for the central limit theorem to apply. And so what we're seeing is we're seeing a histogram of the beta distribution. So if you were to go plot this equation here, with alpha and beta being 0.5, it would look like this, okay? Now let's just take a minute to absorb this, okay? The normal distribution goes from minus infinity to infinity, and it has a peak in the middle. The beta distribution goes from 0 to 1 and has a peak at 0 and a peak at 1, all right? So for my next magic trick, I'm going to make this 0 to 1 with 2 peaks become a minus infinity to infinity with 1 peak, right? That's a real magic trick. Okay, now let's start with n equals 2. So let's go through the code here. So I wrote down n equals 2. So I'm going to sample x's 1000 times. So I'm going to compute these averages 1000 times. There are these sums. So here is my first random variable. Here's my second random variable, and then I compute the average. Remember, to get the central limit theorem to apply, you have to average random variables or sum random variables. So I sampled once, twice, then I took the average. Now look at the histogram, okay? Now it still goes between 0 and 1, right? But now we have a peak in the middle. Now why do we have a peak in the middle? It's because if you take something, there were zeros and ones, those were the peaks originally, but if I take two of them and take the average, the peak will end up in the middle, right? So that's how the 0, 1 peaks became a middle peak. So n equals 2, if you just, if you squint, you might think that looks a little bit like the normal distribution. Okay, so we took two random variables, summed them, and now that is going to give us something that looks maybe a little bit like like the normal distribution. Okay, so now we go to 25 samples. Now inside of my for loop here, I'm going to use a little bit of a trick here, is that if I call Skippy stats and I put this size equals n, then Skippy stats will give me n random numbers. So each time through the for loop, I get 25 random numbers, and then I take the average. Remember, for the central limit theorem to apply, we just have to take an average of random numbers. To actually observe that the central limit theorem is applying, I need to repeat this a whole bunch of times to look at the histogram. So you don't need to do this. You don't need to histogram to know the central limit theorem applies. I'm teaching you now that it applies when you take, an n equals 25. You take the random variable average with 25 of them. For the purposes of this lesson, we're going to be doing this 1,000 times so we can look at the histogram to verify for ourselves that the central limit theorem applies. Okay, so if you're doing, a problem, or you're thinking about statistics in life, you don't have to have 1,000 examples, right? You could only do one example and you'll just know that the central limit theorem applies. But to see it, we're doing this 1,000 times. Okay, so we did 1,000 times. We took the average of these random variables, and look at that, right? Now we're starting to see something that looks like this, the normal distribution. Notice that, just from looking at this, you couldn't tell that the domain of the random variables is 0 to 1, right? Like you could look at this and think that, hey, maybe it extends out to minus infinity, or maybe it extends out to positive infinity. It's hard to tell because we don't have a lot of samples. We only have 1,000 samples. But you're starting to see, from the previous one, this one looked a little bit flat and very sharply peaked. Now we're getting something that looks more like a normal distribution. And so in fact, this is, if you start to look at the properties, if you look at the mean and the standard deviation, you look at the kurtosis, the skew, these different um, descriptors of what a histogram looks like, it looks very, very similar to a normal distribution. So that's pretty incredible, right? Okay, so that was a beta distribution. So the beta distribution is continuous, and it had a sample space from 0 to 1. But here's something impressive. I didn't say that the central limit theorem only applies to continuous random variables. You can actually take discrete random variables. Like it could be events, or it could be the binomial distribution. It still applies. Okay, so let's take a look at the binomial distribution. So now we're gonna up our game. Now these R's are going to come from different binomial distributions, right? I didn't say they have to be from the same distribution. They're from different binomial distributions. So think about this, is that, you wake up in the morning, you play, you flip 5 coins, you record the value, then you play 3 games of chess with your girlfriend and you record how many you won. And then after that, you go online and play, I don't know, League of Legends, and you record how many matches you won in 6 hours. And then you call up your 5 best friends and record how many of them, answer the phone. If you take all of those numbers, completely unrelated, and you compute the average, that will be normally distributed, even though each individual thing is discrete. Okay, that's what we're going to show here. So we have different binomial distributions. We're going to take n of them and take the average, and I'll show you that it turns out to be a normal distribution. Even though each individual thing is a discrete number, the x will be continuously distributed. All right, now the code is going to get a little bit more complicated, and the reason why is that I have to make all the distributions. So I have an n saying the number of distributions I have, right? Because I'm going to have each random variable is going to be from a different binomial distribution. So the first thing I do is I make a couple probabilities of success, right? If I have different binomial distributions, I need different parameters. So I get some p's, okay? So remember, we need to specify p and n for the binomial distribution. Since I'm using n to indicate the number of random variables, I'll use m to indicate the number of trials in my binomial distributions. So I make n p's, right? So these are the probabilities of success. Maybe when I play 3 games of chess with my girlfriend, she's really good at chess, so my p's are very low. But then when I call my friends, they're always ready to answer the phone, so I have a high p there. Then I have my M's, right? So how many games of chess do I play with my girlfriend? Then how many League of Legends games do I play? And then how many friends do I have to call? So some M's and some P's, right? And there's no reason why I did this, but I just made it so that the M's are between 1 and 15. You could make them between 1 and 100, it doesn't matter, but I just made them vary from 1 to 15. These P's are random numbers between 0 and 1. Okay. Then again, I have an array to store my X's. Now I have two loops, right? The reason I have two loops is that I go over all the X's, right? This is that part where I want to histogram X, so I have to do this a whole bunch of times. Then what I do is I sample from my N distributions and I sum them, and then I divide by N. Okay, so this is where I take the average over those beta distributions. So I look at my N binomial distributions. I look at my N of them, and then I compute the average. Okay, if this code doesn't make sense to you, or you're having trouble following it, that's okay. Just understand that what this code does is it simulates the process of averaging over some binomial distributions. So here I have one binomial distribution. So I'm histogramming this. Now, obviously with one binomial distribution, the histogram of X is going to be the same as the histogram from a binomial distribution. Okay, so this is a binomial distribution histogram. So nothing, no central limit theorem here, right? Because N is 1. Now if I go to N is 5, okay, so central limit theorem we wouldn't say really applies here, but we're moving up to 5. Now look at this histogram. This is so fascinating. Remember that the constituent binomials, like the random variables that are making up X, are all discrete numbers. They're all like 1, 2, 3, 4, right? But then when you histogram them, you start to see a binomial distribution. And why? It's because if you have a bunch of finite numbers and you take their average, you can get numbers like 3.2, right? Because if you add up, I don't know, maybe if you add up 1, 3, and 7 and you divide by 3, you get 3.2. But there's certain gaps here. And the reason why is with only 5 integers, when you have 5 numbers, you can't make every possible continuous number, right? It turns out we can't make 2.5. And now the fact that 2.5 is not there, that's just a consequence of what M and P was. I don't know what M and P was. I didn't print them out. But so with these 5 binomial distributions, we can make a lot of numbers, but not all of them. But what's really striking is how much it looks like a normal distribution. And notice that we don't see the fact that the domain is finite, right? Like with 5 binomial distributions, and each one can have up to 15 trial numbers. In principle, you could get 15 as the highest possible number, but notice we don't see things out here. It's starting to look more like a normal distribution with those short tails. Okay, n equals 25, and look at that. I used the kernel density estimation thing we learned from Unit 7, and it looks almost exactly like a normal distribution, really close to a normal distribution. You can see that there are certain numbers here, like 3.82, something like that. There's no way to make it with these 25 binomial distributions, but you can see that we're very close to a normal distribution. So, central limit theorem, even if they're discrete, even if their domain is not the same domain as a normal distribution, they start to approximate a normal distribution. Really powerful idea. All right, so let's look at some examples in real life and see how the central limit theorem applies. Remember the two ingredients. It has to sum. You have to be doing a sum or an average, or you need to have a sum in there. So obviously you could sum and then square it. You could sum and then take the natural log or whatever, but the central limit theorem should apply as long as you have that sum in there. Okay. Actually, I'm not sure if it applies if you sum them and take the natural log. Let's not use that one. Let's just say if you sum them and then divide by n or multiply by n or anything like that. As long as you have a sum and then some constant multiplied by it, it will apply. So you take the yearly rainfall in 25 counties in Rochester and compute their average. So we have 20 to 25 of them, and we're computing the average. So CLT definitely applies. You compute the average rainfall in a particular city over the last 25 years. So in this first example, basically each county maybe has a slightly different amount of rain, so it has a slightly different distribution. So it's just multiple different random variables, and you're computing their average. Here, over the last 25 years, then now each random variable is from the same distribution, so the city has the same distribution of rain every year. Assuming climate change is not real, but climate change is real, so maybe this, it's changing a little bit, but it still doesn't matter. The individual random variables can be different, distributions or the same distribution, it still applies. So compute the average rainfall in a particular city over the last 25 years. Okay, so yes, should be normally distributed. You have 20 temperature sensors placed inside of a batch reactor and you compute their average. You have 20 random variables. They could be in different spots, so they have different distributions, but still you're computing their average, so it applies. Okay, you measure the weight of 25 chemical samples. Okay, this one's kind of a trick, right? We measured the weight, but we didn't take the average. So we actually have 25 numbers here, but we didn't do an averaging or a sum. So no, the central limit theorem doesn't apply because you didn't, you know, take the average or do any summation. You eat 25 random candy bars per day and sum up their calories. So we're not taking an average here, but we are doing a sum, so it still applies. So the number of calories you eat per day would be normally distributed. It would be horrendous, and I don't recommend doing it, but it would be normal. But I mean, normally distributed would not be normal. This is not normal behavior. Your scale is inaccurate due to 20 sources of error. Assume the error is additive. You measure the weight of something. Okay, so this one is kind of getting at a real engineering thing, is that if you build a scale, you have like error because, you're bad at putting stuff on the scale. There's error because there's electric components on there. You have air pressure, you have convective currents. Maybe the calibration was a little bit off. Maybe the electricity coming on the wall is oscillating up and down, so your voltages are a little bit off. Maybe the thing that displays the numbers a little bit off. Maybe the spring on the scale, one of them is a little bit different than the other three. But if all of the error sources are adding up, so each of these errors is adding up, then you can assume that you have a bunch of random numbers adding together to result in your actual weight that you measure. And this shows that the error is going to be normally distributed because each of the component errors may be not normally distributed. Convective currents are not normally distributed, right? And the problem with the electrical circuits might not be normally distributed, but when you sum them all together, the error becomes normal. And that gets at the real key engineering consequence of the central limit theorem, is that all error sources, or almost all error sources, are normally distributed in engineering. And so that's why the normal distribution is really key to know, and that's why probability theory applies to the real world, is because most sources of error are normally distributed. I'll mention one caveat, is that sometimes the error sources multiply with one another. Then it becomes log normal. Okay, but we're not going to look at that right now, but just, so it's the same kind of principle, is that when you have a bunch of sources of error, they come together to become normally distributed. Really powerful idea. So definitely central limit theorem applies. Okay. Your scale is not normally distributed. Each time you weigh something, you weigh it 22 times and take the average. Okay? Now, this one is just a little bit weird. Okay, so we're saying that we have a random variable that we're looking at, and we say that it's not normally distributed. That's fine. And then each time we weigh something, we weigh it 22 times and we take the average. Now, as long as your scale gives you a slightly different weight each time, that is, each time we weigh it, we get a slightly different random outcome, then yes, when we take the average, it will be normally distributed. However, it might be that if you weigh something, you're actually just getting the same random variable. Like, you're not actually getting a new random variable. You're just seeing the same random variable 22 times. So then it's not actually n is 22, it's n is 1. You're just multiplying it by 22 when you sum it together, or you're just, taking the average of something by itself. So this one kind of depends, but I would say in principle, if your scale is giving you, if it's a random process to weigh something, like whenever I weigh my son, he my little tiny 1-year-old, he likes to walk on the scale and spin around, put one foot on the scale, one foot off the scale, right? Or he likes me to hold him. So yes, it is a random process and it would be normally distributed. Okay. So this one kind of depends on the process, but I think yes, in general it applies. All right. So that's about the central limit theorem applying. Okay. And like I said, it's a real key result in probability and statistics. So now we're going to look at something even more important. And I would say this, well, I should say more important, but this is the main or the most important consequence of the central limit theorem. And that is when you compute sample means. Okay? So we know from the law of large numbers that if I compute a sample mean, if I have a big enough sample, it should approximate the true or population mean. Okay. So when I say true, I mean there is some true normal distribution. We're gonna use the word normal throughout this lesson, but most of these what I'm going to discuss applies to other distributions, and I'll talk a little bit about that later. But for now, I'm just going to use the word normal. So like let's say I'm trying to estimate the weight of people in the U.S. If I were to look at 10 people in the U.S. and compute a sample mean, the law of large numbers says that as that gets larger, so not just 10 people, look at 100 people, look at 1,000 people, I begin to get at the true normal distribution of the entire US. Now we're going to use the word population mean, and that is like if I could measure everyone in the United States, I would obviously get the true mu, what the true mean is for the United States, or the true expected value, I should say. So when I say population, it means the one from probability theory. So population mean is a synonym for expected value. Why do we say population mean? Well, one reason is that it's historic. Another reason is that sort of the ideal case is if you could grab everyone that makes up the population, right? The sample is some subset of the population. If I could get the population mean, that would be the same as the true expected value. Okay, so whenever people say population mean or population variance, they mean the true probability expected value and the true probability variance. And then when we say sample mean or sample variance, that's coming from some small subset that we were able to obtain. Okay, so that's the setup. So here's the setup, is that we want to take sample means, and the law of large numbers says that the sample mean approaches the expected value, but we're going to actually see if we could do better, right? Law of large number gives us no sort of guarantee about how fast that happens or what n needs to be. We're going to try to use the central limit theorem instead to see how sample means approach population means. And this is a really big deal. Like I think actually this is probably one of the most important issues in this coronavirus outbreak is that people have to use sample statistics, like they look at the people in the hospital and they compute how many people die, and they try to estimate what the case fatality ratio is, like how many people die if everyone is infected, or what is going to be the probability of death for everyone. And you have to only sample, right? We can't just actually go test everyone, see how many people have it, and see how many people died. You have to take some small subset. And it's a big deal because people have to make policy decisions. Governments have to decide whether to open or shut down based on these samples. So sample statistics, it's a real big deal today. Okay, so here's the game. The game is we are taking sample means and we want to know about how they are distributed. That is, if we go randomly sample 5 people and test them for coronavirus, or we sample 5 people and we measure their height, we don't expect it to be a deterministic process, right? Because the 5 people we chose is random. So we want to know what is the distribution of the sample mean. So I take 5 people, I do it over and over again. How does my sample mean look? Now you hope that the expected value of your sample mean is the same as the population mean. We hope that's true, right? Because otherwise, when you're sampling stuff, that's weird. But yeah, we hope that if we look at 5 people, that on average, like we should never be a little, we should never be more higher or lower, but on average, it should be, on average the same as the population mean. Okay, so let's look at this distribution. So we're looking at, and this is why the central limit theorem applies, is that our sample mean is it's an average. It's a mean. So it's taking a sum and then doing 1 over n. Okay. Now then the central limit theorem applies, if you have 20 to 25 people. Okay, so that says that the probability of the sample mean, the probability of seeing a particular sample mean, is normally distributed. Okay, so that's big. So this is number one. It's normally distributed. But what we want to know is, number two is how is it connected to the population statistics? Is the probability of a sample mean, is the expected value the same as the population mean? What about the variance? If I take 5 people and I compute their sample variance, how is that related to the population variance? Okay, so the central limit theorem provides a little bit of glue to connect these two concepts. Okay. So let's talk about what P of x bar looks like. We know it should be normal, right? The central limit theorem tells us that. But what about as n, right? We said if n is big, then the central limit theorem applies. But we might see that n has a more of an effect than we want. Okay, so like we just did for the central limit theorem examples, I'm not going to try to derive anything. I'm just going to write a computer program, a Python program, and just see what happens. Okay, so Again, this code is a little bit complicated, but I just want you guys to get the key idea. So I wrote this as a function this time, but it's the same as before. We're going to simulate the process of computing sample means. So let's take a look at what the function takes. The first thing is the mean. This is the population mean, the true hidden mean we're trying to find. So we're trying to find this number, okay? Now, obviously I know it because I wrote it down, but we're trying to simulate the process as if we did not know it. Then this is the population standard deviation. Again, I don't know it, and that's what we're trying to get at. Bins here, this is going to just be the histogramming. So at the end of the day, I'm going to histogram it, so we don't need to worry too much about this. And the samples here is uh, how many times we're going to simulate this process. Okay. And so, I'm going to try this 10,000 times. And again, this is like not real. This is just me. I want to look at how X bar is distributed. So I'm going to do this process a whole bunch of times so I can histogram it. This has nothing to do with how you would actually take samples. Like this samples here, it's a misleading number. It's not the actual samples for like computing the sample mean. This is how many times I'm going to repeat this process. N here is how many people I'm going to look at a time, if we think about this as a people problem, or how many samples I'm going to look at a time. So we're going to go through 10,000 times and grab n random samples, and we're going to compute their average. And we're going to do that a whole bunch of times, and we're going to histogram to see what those sample means look like. We compute their sample mean. So I'll just quickly go through the code. This is where we're going to store the data. We're doing this 10,000 times, so this is my for loop. We create the samples, and here's where we put the population mean. This is what the population mean and the population standard deviation are. So this is a probability, a normal distribution. So its expected value is the mean, and its standard deviation is the standard deviation given here. And we're getting n of them, right? Where we want to know about how n and the population mean and this relationship between them. We know it's normal. I'll notice that this is normal. I'm saying that the underlying data is normal, but the central limit theorem tells us that resulting this thing here, when we are after we're done taking this mean, it will also be normal. This is taking the mean, this is putting it into this array, and then this is just plotting it, okay, or taking the histogram of it. So let's see an example. So our population mean is 2, okay, and then let's see what the histogram looks like. So this is my sample mean, and you can see that the population mean is 2, and my peak is maybe like 2.1. So that means if I try this, a whole bunch of times, my sample means are pretty close to the population mean. Okay, and that's good. That means that if you go out and you take 25 people and you measure their weight, if you do this a whole bunch of times, your sample mean should give you the population mean on average. Okay, now obviously if you pick 25 people and you're unlucky and they're just some, odd set of 25 people, you might get a, higher sample mean than the population mean. But you're equally likely to get 25 people and they just happen to be very low weight people, and you're equally likely to get a little bit below the population mean. But on average, you should get, the center, it should agree with the population mean. And it's normally distributed, okay? And that's coming from the central limit theorem. The fact that this is normally distributed, it's not because the underlying data is normally distributed. It's not because weight is normally distributed. This is about the sample mean. We're talking about sample means. I'm not talking about people's weight. I'm talking about me going and randomly picking 25 people, computing the sample mean, and then seeing how those sample means are distributed. So each point here, each little point on this curve, this is not an individual's weight or the probability of an individual's weight. It's the probability of getting a sample mean. It's the probability of looking at 25 people and getting a, when I compute their weights and I get 1.1. Okay. Whew. Okay, so if you understand that, then the rest of this lecture is going to be easy. So if you don't understand that, think about it. Okay, so this x-axis is not like a individual person. This is not somebody's weight. This is not, the sample. This is the sample mean. So we're doing randomly picking 25 people, computing a sample mean, and then this is the resulting histogram of that process. Okay, so what have we learned? We learned that sample means with n is 25, it looks like it's normally distributed. And we saw that the center of the distribution, the expected value, is approximately the population mean. And that's correct. You can analytically show that. So if you go out and you measure the sample mean, then the expected value for that, will match the population mean. And that's great. That's good news. That means the idea of going and taking a sample from a population and computing the sample mean, that gives you insight into the population mean. That's good news, right? That's exactly what we want, right? If that didn't hold, oh boy, we'd have a lot of trouble. Okay. But we don't know anything about standard deviation yet. We don't know about how n matters. So let's go a little bit deeper, okay? A little bit deeper. So now what I'm going to do is I'm going to change the population standard deviation, okay? So I'm changing the population standard deviation. So I'm not changing, n, I'm not changing the population. I'm just seeing what happens to the population standard deviation. So remember that my distribution, what we're histogramming here, is how the sample mean changes. So we're saying if we go back to the weight example, we're picking 25 people out, measuring their weight. If I make it so that people have higher variance in their weight, like everybody eats 25 random candy bars a day, so people's weight varies a lot more, then the distribution for the sample mean also varies more. And this makes intuitive sense that if your population varies more, then when you try to grab 25 samples and compute their sample mean, you get more variance, okay? So this is not anything about how we do the process. It's nothing about how we sample or how we compute the sample mean. This has to do with the more, the more randomness intrinsic in the population, the more randomness we get in our sample mean distribution. And you can see, if we have a population, a very low standard deviation population, we get a very narrow peak. Now, this is always good. This is a good question, unrelated. But do you see how we're seeing numbers here that are 1.8, right? How is that possible? It's because if you have a distribution, what we're looking at here is something that is continuous, right? So if you see, oh, hey, how come we have a probability of 1.8? It's because you have to integrate over this, right? You have to integrate over this to get a probability. So even though we see numbers greater than 1 here, that it doesn't have anything to do with probability, that's probability density. So if you're wondering why this is going above 1, it's because of probability density. Okay, and this code up here just is to make the plot. Okay, it's still using that hist means function we wrote a second ago. Okay, so we could guess, and it's a good guess, that the standard deviation of the sample mean is the same standard deviation as the population standard deviation. Okay, we're going to find out it's a little bit subtle, but it's true. If you have the population standard deviation, if you know the population standard deviation, then your sample mean has the same standard deviation. Okay, that is again a great result. So that means if you know the population standard deviation, then if you go take a sample, the standard deviation of your sample mean will follow the standard deviation of the sample. Now, it's not quite exactly there, it says proportional to. We're going to clean it up a little bit, but basically they're related. So if you get this population standard deviation, it's related to how spread out your samples will be. Okay. So then one of the things we're going to do is we're going to see, can we basically correct for that? Can we basically take all of these different distributions, and if we divide by the standard deviation, okay, we know that if we can divide by the standard deviation, do they all line up? And if they do, that's basically like converting all of these normal distributions that are, by sigma and mu, we're going to basically collapse them onto one another by dividing by the standard deviation. So this is maybe a little bit harder for you to grasp, but this is just checking, is our guess correct? Is our guess correct that if we know sigma, then all of the distributions, we can basically account for how sigma is changing. So what I just did is I went on this plot and I divided everything by their standard deviation, and that completely corrected for the difference between them. So that tells me that this guess is correct. Okay, so if you know the population standard deviation, or if you know these mu and sigma, then you know how the sample mean will be distributed. Okay. Okay. But what about n? So now we know population standard deviation determines the sample mean standard deviation, and the population mean determines the sample mean expected value. Okay. Now what happens as n changes? This is really fascinating. So as you can imagine, if you go grab 5 people versus you grab 100 people, your sample mean will vary a little bit more. Okay, now I'm plotting now, see how it's centered at 0? I'm not plotting the sample mean now. I'm plotting the distance between the sample mean and the population mean. So if it's 0, that means that my sample mean is going to match the population mean, right? So it's basically how far off am I from the true population mean? And you can see that as we get more samples, we fall right on the population mean. And this makes sense that if you grab more people for your sample, you'll more accurately represent the population mean. And if you only look at 5 people, you're less accurate in matching the population mean. And so this is sort of the correction here is that, for a given n, this is true, but as you change n, this happens. Okay. So then this is now completely correct, is that how wide this is, how much you vary, depends on both the intrinsic variability in the population and the square root of the number of samples. This is a very sad consequence of life. This is kind of a roller coaster of emotion. Central limit theorem, thrilling, helpful. It changes everything about statistics and engineering. It's so critical. It enables so much analysis in engineering. That's how we compute things like risk factor, how we can be sure a bridge will stay up. It's how we can be sure that a plane will fly, because we can compute all of these complex individual random things. They combine to make normal distributions, and then we know how to deal with those. Another thrilling thing we saw is that sample means follow the central limit theorem, and their mean follows the population mean. That gives this whole idea of, like, if you want to know if people are likely to vote for Joe Biden versus Donald Trump, you only need to call up a couple hundred people and you'll get at the correct answer. But and then this is great, that if the population becomes more varying, then your sample mean will also become more varying. I mean, obviously it's not great, but it makes sense, right? Like, you have more variation in your population, you have more variation when you try to approximate the true mean. So then this is the sad thing, is that if you want to remove uncertainty in your sample mean, that is, you want to basically make it so you're more certain about what the population mean is, right? You're trying to connect this to this. You're trying to connect those two. It goes down by the square root of the number of samples. So that means if you want to be twice as certain, you need 4 times as much data. If you want to be 10 times more certain, you want to be from, an uncertainty of 0.1 to a certainty of 0.01, or an uncertainty of 0.1 to an uncertainty of 0.01, you need 100 times more data, 10 squared, right? If you want to be, 1,000 times more certain, you need 1,000,000 times more data. So this consequence that it's a square root of n is very disappointing. And this is something that, is a big deal in engineering, right? So, like, if you want to have more signal, if you want to approximate something more accurately, you need to have a square times as many more samples. Um, an example is something like GPS, right? GPS, you have satellites flying overhead and you want to use them to approximate your position. This is not so important anymore, but when GPS first came out, like, it was really slow and buggy. Like, you had to sit there for 20 minutes or something until your GPS signal figured out where you are. And the reason why is that the signal was very weak in GPS. So you had to get lots and lots and lots of messages back and from the satellite. You had to get a lot of messages from the satellite before you could finally figure out where you were. And it came down to this square root of n thing, is that to be more accurate, to get you accuracy at, like, the foot level, you needed thousands and thousands, probably million samples. And that comes all down to the square root of n. So, this is great. We're happy about this, but the square root of n, that's a big deal. So when you do sample statistics, to increase your accuracy, it goes by the square root of the number of samples. Very sad result. Okay. Now, I've kind of been hinting at this, but what we usually think about is we don't usually think about the distribution of the sample mean. We usually think about how far off are we from knowing the population mean. Okay, so that is, I go compute my sample mean. Now I have an estimate for the population mean, and we want to know about how far off I am. So this is kind of a mathematical rearrangement. So on average, I'm, perfectly on the money. If I repeat this process a whole bunch of times, the average, I will on average be above the population mean and below the population mean, so it's symmetric. But this term here, the second term, this is more important. That is, how far off I am in my estimate for the population mean depends on the intrinsic population variance and the square root of n. Okay, so we're going to talk less about this sample mean probability and more about how far off I am from the population mean. Okay, so one of the things people like to talk about is the standard error. So standard error is basically a way to account for both the population standard deviation and the square root of n term. So if we talk about standard error, we're talking about some sample. We have a sample, and its standard error is going to be the sigma over square root of n. And this just gets at the fact that usually we need to think about both the number of samples that make up the sample, or the number of samples. Yeah, the number of samples is the number of data points we have in our sample, and we need to know about the population standard deviation. These two things are called the standard error. So let's see if we have one more slide on this. Yeah, but basically then if we talk about the uncertainty and our population mean, our uncertainty in knowing the population mean, it has a standard error. So instead of a standard deviation, we call it a standard error, and that just accounts for this n. Okay. So let's get a little bit more numerical. So first of all, let's just discuss the expression here. So here is the actual probability distribution. So I'm just expanding out, if this is it's a normal distribution centered at 0, here's this equation. And then let's plot this equation that we have, right? This is our equation that we have. Let's plot it and compare what we got with the histograms, right? So this is, we've basically I've given you a reason why that's the right equation, but let's take a look. So you can see that it follows really well, right? So this is what we did with our Python program, and here's our analytical equation, and they match. So our simulated example matches our analytical equation, so that's good. So let's see an example. Okay, let's see an actual numerical example. Let's say that I know, maybe I talked to my manufacturer of chemical balances, but somehow I know that the population uncertainty, the population's error is 0.2 grams for a chemical balance. Okay, so I have chemical balance, and in general, it has an uncertainty of 0.2 grams. And then I'm using that chemical balance to calibrate my micropipettes. This is actually a real thing. Like if you want to calibrate your micropipettes, which is really important if you're working in a biochemistry lab, you calibrate them by weighing water. So what you do is you put water in your micropipette, and then you put it into the chemical balance, and you weigh out to see how much water you got. So I weigh out 1 milliliter of water 20 times with a micropipette, and I weigh it with a chemical balance. And so to calibrate it, you make sure that you're getting out 1 mil of water by weighing the water. So my sample mean is 1.001 gram. And so the question is, what is the probability that the true mean of the micropipette is within 0.001 grams of the sample mean? That is, I know that it should be 1 gram because 1 mil of water is 1 gram. So I'm asking, what is the probability that it actually falls into that? Okay. And so to turn this into a mathematical statement, I'm saying, I know this is normally distributed with this expression here. This is the standard error. So I gave standard deviation, right? So 0.2 over the square root of 20. I just wrote this kind of a funny way, but it's 0.2 over the square root of 20. And I want to know, what is the probability that the distance between the 1.001 and the true population, which I can observe, although secretly I know it's 1 gram, what is the probability that it falls within 0.001 grams of this number? Okay, so I want the interval between minus 0.001 and 0.001. Why is it from minus 0.01 and 0.01? Because we're centered at 0. So in fact, I didn't even need to tell you this, you didn't even need to know what this number is. This number has nothing to do with the problem. It's just asking about, what is the probability that we're going to fall within that interval, right? Because this distribution is centered at 0, so I didn't need to tell you this. Okay. So this is an integral. We can just get z values out. So the z value for the bottom of the interval is minus 0.001. The z value for the top of the interval is 0.001 over the standard error, right? Remember the z is mu minus x over sigma, and sigma for our distribution is standard error. So it's this, right? This is our standard deviation. And so we get a 1.8. Okay. So what that means is that there's a 1.8% probability that it falls within that interval. So that's a pretty low probability. That means that me saying that I'm within 0.001 of the true population mean, that's not a very correct statement, right? So that says that the population mean is going to be at between 1.001 and 0.999 1.8% of the time. So as far as my calibration goes, the the actual this could be far off because the true population, I mean, there's only a 2% probability it ends up right between these numbers. Okay, so what does that mean? It means that basically, uh, you shouldn't be thinking about this much precision. This 0.001, this one here, we're not that precise because our 0.2, right? This is the uncertainty, and as you can imagine, right, like that's in this decimal place. And that's reflected here is that, our actual boundary, our probability for the population mean falling within this interval is actually quite low. So the population mean could be in many other spots, right? There's only 2% chance it's in here. That means there's a 98% chance that the population mean is not in this interval. Okay, so, this is we're going to get into a little bit more detail about what this means, and this is something called a confidence interval. But for now, just thinking about this in this example, there's only a 2% chance the population mean is in there. Put another way, there's a 98% chance that our true population mean is not falling in there. All right. Okay. Now, it's pretty rare for you to actually know the population's standard deviation, right? Like I said in the previous example that maybe I knew the manufacturer and he told me what the population standard deviation is. So in practice, you're usually estimating both the sample mean and the sample standard deviation. So in practice, you're actually estimating both. So let's see what are the consequences of trying to estimate both of them simultaneously. So this makes our life harder, right? We are no longer just grabbing a sample and calculating the sample mean. Now we're calculating the sample standard deviation. So I'm changing my code a little bit here. This is this make hiss. So now we're going to try to estimate the sample standard deviation and the sample mean. And this code here is very interesting. Okay. So what I did here is that I did that same trick where I tried to divide everything by the standard deviation to remove the effect of the standard deviation. Okay, remember before, let's see if we can go all the way back to that. No, well, I guess I can't go back to that. So before what I did was if I divided by the population standard deviation, all these lines line up. They all line up. But if I have to estimate both the sample standard deviation and the sample mean, that turns out that they don't actually line up. It turns out if you look at n equals 3, my estimate for the sample standard deviation is a little bit too low. That is, when I try to estimate the sample standard deviation, it turns out that n has some role. Okay, so when we compute the sample mean, it just approximates the population mean very well. It turns out when we compute the sample standard deviation, it does not just approximate the population standard deviation perfectly well. There is an effect of n. That is, the more samples we have, the better we approximate the sample standard deviation. And the less samples we have, the more we underestimate the population standard deviation. So this creates a complication. When n is big, when we have 20 to 25 samples, it's normally distributed and everything is fine. So when we have 20 to 25 samples, we just basically do get the correct answer if we compute the sample standard deviation. So everything we just described above, like that example with the chemical balance and everything, if we have 20 to 25 samples, you can do that problem, the chemical balance problem, without knowing the population standard deviation. You can just approximate it with a sample standard deviation. But if n is not big, the central limit theorem does not apply. It turns out that it follows a different distribution called the student t-distribution. And it's very much like a normal distribution, but there's an extra parameter, and that extra parameter is the number of degrees of freedom. Okay? So this is like a normal distribution, but it gets a little bit more spread out as n changes. Okay? Now, where do we see the student t-distribution? So we're not saying that the population follows the t-distribution. We're not saying that, the underlying data follows the t-distribution. We're saying that if you try to compute the probability of how mu differs from x bar, that is, you're computing how far off your sample mean is from the true population mean, that distribution follows this. Okay, so notice here we're using the sample standard deviation, and we have to put in this n minus 1. Now, if you knew the population standard deviation, if you knew sigma, then you don't need this t-distribution. You can just use the normal distribution with sigma here. But if you have to estimate both the sample standard deviation and the sample mean, then you have to use this t-distribution. You have this extra parameter. Okay, we're not going to look at the equation. By the way, this just shows that it works. We're not going to look at the equation for the t-distribution. It's just going to be a SciPy function we call. All right, just a SciPy function we call. This is just some summary of the lecture. We'll see in the next lecture what that means practically. But basically, there are two things that happen. We want to know where the population mean is. Okay, we want to know how to estimate the population mean. So we do that by taking a sample. Okay, so we go grab some data, we take a sample. What we're saying is that if you know the population standard deviation, then the true mean, the population mean, will follow a normal distribution centered at your sample mean, or vice versa. You can say the probability of your sample is going to be centered at the population mean. These are interchangeable, right? But the way it varies is going to be normal, and it's going to be with the standard error term. So the population standard deviation divided by the square root of m. So if you want to talk about how accurate you are at estimating the population mean, it follows these statistics. But if you're estimating both, you don't know the population standard deviation. If you're estimating both the population standard deviation and the population mean, then you compute your sample mean and you compute your sample standard deviation, but you have to use a t distribution instead of a normal distribution to account for the fact that you're approximating these two things simultaneously. And then that extra parameter of the t distribution is the n minus 1. Okay, so this lecture covers two things. One is the central limit theorem, which is this great result that tells us whenever we take sums and averages, we get a normal distribution. The second part of this lecture tells you about if we approximate population means, which is a common task in engineering. We want to take a sample of some larger population. Like if we're doing quality control, we only want to look at a few things from the assembly line. Then the central limit theorem helps us by connecting the small number of samples to what the true population statistics are. And the connection between them follows this equation, that the probability of what the population mean is follows this t-distribution. And if you have n is 25, then this t-distribution disappears. If you have n is 25, then this becomes normal again because the central limit theorem applies. Now, it's never wrong to use the t-distribution. You can always use the t-distribution with n is 25, so it's totally fine. But you can basically replace it with a normal distribution with n is like 25. Now, something we didn't talk about, and this may be a question, is that what if you want to know how to approximate the sample standard deviation? What if I want to know how far off I am in this? We're not going to cover it in the class, but basically all we're going to cover is this is describing how far off we are about the population mean. Okay, so that concludes lecture 1 in Unit 8. In lecture 2, we're going to see how to practically use this result. We're going to see how to use this result. This is the analytical equation. So I think this lecture is important conceptually, and it's important to understand where this comes from. But as far as practical things like doing your homework and your exam, the key from this lecture is about when and how the central limit theorem applies. Then in the next lecture, we'll see practically how to use these equations we sort of derived about the connection between population mean and sample mean. All right, see you guys later.